Hello, osmosis energy modelers. Today we're going to look at how to introduce emission policies into osmosis models. First, if you come to this Zenodo deposit, which will be linked in the description down below, you will find the exercise we're going to run through today. Also in the Zenodo deposit is a base ClickSense file you can download to follow the exercise. There's also a data helper file to help in completing the exercise. The first thing we're going to do is download the exercise in PDF form. So before working through the exercise, we're first going to give an overview of what we're going to learn through completing this exercise. So the learning outcomes for this exercise are to 1. Understand the different emission policy options available in osmosis. 2. We're going to implement an emission penalty in an osmosis model. 3. We're going to implement a yearly emission limit. And 4. We're going to implement a model period emission limit. So as we learned in a previous lecture, osmosis exposes a few emission parameters to the user, and these can be classified into quantity-based emission policies and price-based emission policies. So the emission penalty is a price-based emission policy, and this is where we decentivize the model from producing emissions through taxing each unit of emission released. This is different from the quantity-based emission policies such as annual emission limit and model period emission limit, where we constrain the model by restricting the amount of emissions the model can produce either each year or over the full time horizon. So the emission penalty parameter, a thing to note with it, is that it does not constrain the model. It just decentivizes the model from producing emissions. What this means is that if you have a model that only, for example, has a single coal power plant producing electricity, that coal power plant can still produce as much emissions as it wants, given whatever emission penalty you put in. So while the emissions may grow and the cost might grow, the model will still remain feasible. This is different than the quantity-based emission policies, where we actually constrain the model. So for example, in the quantity-based emission policy, annual emission limit, we define a curve for over the horizon for each year, saying how much emissions can be released in that year. So for example, if I want to linearly decrease my emissions from the start of my model run to the end, I would define this red curve that says for each year I can only produce X amount of emissions. This curve can be whatever I like. So if I wanted an exponential decrease in emissions, I could also define a curve that looks like that. So this is the annual emission limit, and this is different from the model period emission limit. In the model period emission limit, you define to the model over the total horizon of the model how much emissions can be released. And then the model will define the optimal curve on how to reduce those emissions, given that restriction you implemented. So this may actually mean in the first couple of years you see an increase of emissions to reduce the amount of stranded assets in your model, and then you see a sharper decrease later on. These are the 3 main types of emission policies available in osmosis, and we'll now look at how to actually implement these in models. So the first thing I need to do when investigating the use of emission policies is to understand how the model is naturally behaving with the current emission policies. So this involves running a reference scenario. So for this reference scenario, the objective is for a government is interested in exploring different emission reduction policies, and you're contracted out to present different options to see how they reduce system level emissions, with the end goal of being net zero by 2050. So as we said, we first have to go through and see how this reference scenario behaves with current emissions. So I will first come back to the Zenodo deposit, and I'll download this base ClickSense file. This will be our reference scenario. Following instructions in previous videos, I go through and I use ClickSense to generate an Osmosis Cloud data file, and I run a reference scenario. I download the results and I'm viewing them offline. Once I import the results into my offline viewer, I make sure to refresh my results, and this is the reference scenario emissions. So as we can see, without the introduction of any sort of emission policy, our emissions are rising. So I want to be able to compare the emissions across all my different scenarios. So I've created a summary of results Excel sheet here, and we're going to have our different scenarios across the top, and we're going to be able to look at how our different emission policies affect each scenario. So the first thing I'm going to do is I'm going to come back to my offline results, and since we only have CO2 in the model, I'm going to copy the results from the CO2, and I'll paste them into our results template. I'm making sure to paste as values. And we can see this chart now matches what we see in the exercise sheet. A thing to note is that the units of our emissions are million kilograms of CO2, and I want to take a minute to explore how we arrived at the units of million kilograms. So back in the exercise description, we have this note here that says to be careful with units. And if we explore the annual technology emission by mode constraint equation, we can see that it's the emission activity ratio multiplied by the total annual technology activity by mode. In this model, we input our emissions in kilograms per gigajoule of CO2. Therefore, the emissions by mode must be in million kilograms, and that's because we have kilograms per gigajoule as our emission activity ratio. We have our activity in units of petajoules, and if we multiply this out together, we arrive at units of millions of kilograms. It's really important to make sure you double check your units, especially when we start implementing emission penalties and emission limits to make sure our units are correct. The next step is to now implement an emission penalty in the model. So our policy objective will be understand the effects a different carbon tax incentives will have on system level emissions from 2015 to 2050. To analyze these effects, we're going to apply a carbon tax for a moderate and aggressive emission penalty rates. And we're going to compare the CO2 emissions with our reference scenario we just ran. So below, there are our two tables for both our moderate scenario and aggressive scenario emission policies. So from 2015 to 2020, we're not going to implement an emission penalty. Then from 2020 to 2030, our emission penalty is going to be $10. From 2030 to 2040, it'll be $20, and 2040 to 2050 will be $30 per ton. The bottom table can be read respectively as the same. It's important to note units here. So a lot of times policies will be given in dollars per ton. However, we have to make sure our emission penalty matches the units in our model. To do that, if we look at step 4 in the methods, we can see it says to check units of the emission activity ratio parameter. And there's a note below that goes over how to do this. So what we're going to look at is we're going to look at the constraint equation in the model that has emission penalty. We can see that it's the annual technology emission times the emission penalty will give annual technology emission penalty by emission. If we do a unit analysis of this equation, we know our emissions are given in million kilograms, and we know the monetary units in this model are $1 million. Therefore, to satisfy this equation, our emission penalty must be in units of dollars per kilogram, and that's what's explained here. And this is important to note, as emission policies, as we just talked about, are a lot of times given in dollars per ton or $1 million per million tons CO2 equivalent. If we input the emission penalty in dollars per ton, we'll be taxing the emissions 1,000 times more than we actually want to. So we have to be really careful with units. So if we come back to our tables, instead of dollar per ton, we want to input this as dollar per kilogram. So that means all these values we're going to have to divide by 1,000. If we go back to the Zenodo deposit, you'll see there is a data helper file here. In this data helper file, we have set up the values we're going to input into our model. Once opening the data helper, you can see we have our moderate emission penalty and our aggressive emission penalty scenarios here. And as we just talked about, we are inputting values in dollars per kilogram. So this is the value in the table, which is $10 per ton divided by 1,000. We then run these two scenarios on OSeMOSYS Cloud by copying and pasting these values into each model. On OSeMOSYS Cloud, I have already ran these models. We have our moderate carbon tax using the emission penalties in this scenario, and the aggressive carbon tax using the values in this scenario. And these values go from 2015 all the way up to 2050, so make sure you copy in all the values. Once I have run those scenarios, I can come back to OSeMOSYS Cloud and I'll download the result files and view the results locally. So for the moderate emission penalty scenario, this is the result curve for the annual CO2 emissions. And again, I'm making sure once I paste in my results that I refresh my data. In comparing this to the aggressive emission policy scenario, it can be quite difficult to see the differences when the data are on two separate graphs. So I will add both of these data to our results summary chart. So first, I will come back to the moderate emission policy. I will copy all the data for CO2 emissions, and I'll paste this in the moderate carbon tax scenario. Again, making sure to paste as values. And we can see the moderate carbon tax scenario has been added. And I'll do the same for the aggressive carbon tax scenario. So now we have the three curves showing the three different effects of our reference scenario in blue, our moderate carbon tax in orange, and our aggressive carbon tax in gray. An important note here is that while there might be an effect from the emission policy, we are not curbing emissions. The emissions over the model horizon are still rising. Therefore, we want to maybe look at either implementing a more aggressive emission policy or implementing some sort of emission caps. So these would be quantity-based emission limits. And that's what we're going to do next with the annual emission limit. So next we'll flip back to the exercise and we'll scroll down to the next section, which is implementing a yearly emission limit. So the objective for this one is to reach net zero CO2 emissions by the year 2050, with the maximum emissions linearly decreasing from 2020 through 2050. To create the linear CO2 emission reduction curve, we're going to need a few different parameters, and they're all going to follow this equation shown here. So we're going to need the CO2 emissions at our end year, which will be 0. We'll need the CO2 emissions at the start year, which we don't know yet. We need the year at the end, which will be 2050, and we'll need the year at the start, which will be 2020. And then what we're going to do, we're going to solve for the CO2 allowable in each year, following this equation. So the parameter we're missing is the start emissions, this value here. If we flip back to our results summary sheet, we can see in the year 2020, we have roughly 732,000 million kilograms of CO2 emissions. So this is the value we're going to take to be our start year, or our start CO2 emissions. Next, we're going to create the linear curve that's going to define our yearly emission limits. To be able to do that, we have a helpful emission limit Excel sheet set up. And what we're going to do, we're going to use this formula, which is the same one given in the exercise, to create our curve. So first we're going to fill in our parameters. So we know CO2 in the end year will be 0. CO2 in the start year will be the 732,000 from our reference scenario. Our end year will be 2050, and our start year will be 2020. From 2015 through 2019, we don't want to impose any emission limit. So I'm just going to put in 9 nines as to represent a very large number that's not going to constrain the model. Next, we're going to populate this value following this equation. And wherever we reference parameters here, we're going to make sure to lock those references with $signs. So first, we're going to have our CO2 in the end year, which will be 0, and we'll lock that reference, minus CO2 in the start year. That'll be divided by our end year, which would be 2050, minus our start year, which will be 2020. This will be multiplied by our year of interest, so in this case it will be 2020, and we're not going to lock that reference because we want that value to change, minus our start year, which will be 2020. And then we're going to add in our CO2 start emissions, which will be this guy. And this is just the linear interpolation formula. And we can see in 2020, our emissions are 732,000, and that's what it should be. And then we can double click and we'll see our emissions drop each year until we get to 0 emissions in 2050. So that looks correct. And you will also see, if you flip back to the data helper file, these should be the same values that we see in our annual emission limit scenario here. So now we're going to follow the same process as before. We're going to make a copy of our base ClickSense file. We're going to copy these values in for annual emission limit. And in this scenario, we are not going to include an emission penalty. So in our scenario, no emission penalty, only an annual emission limit. We'll copy those values in. We will come back to OSeMOSYS Cloud. We will run the annual emission limit scenario, and we'll download the result files to view the results locally. Once I follow that process, I can come to Excel and view my results here. As expected, we see a roughly linear line all the way down, with the exception being in this section here, and that's where emissions are actually not reaching the limit, so that's okay. Next, we're going to copy and paste in these into our results summary table. Under our annual emission limit scenario, we'll paste as values, and we can see our annual emission limit scenario. We can see the emissions reducing to 0 by 2050 in a linear fashion. Finally, we now want to implement our model period emission limit scenario. So if we come back to the exercise and we scroll down, we can see we have our objective for a model period emission limit. So we need to describe an emission reduction pathway that will produce net zero emissions in 2050 and that will allow no more than 16,500,000 million kilograms of CO2 emissions. And I picked this number because it's roughly 50% of the optimal system emissions, but this number could be whatever you want it to be. So the first step will be make a copy of the reference scenario as always, and then if we come back to our data helper sheet and we scroll down to the model period emission limit scenario, you'll see that we have a time independent variable here. So model period emission limit, again, is defined over the model horizon. so it doesn't depend on the year. So we are going to define our CO2 model period emission limit to be our 16,500,000 value. Also, I want to emphasize that we are no longer implementing the annual emission limit in this scenario. You can, if you like, implement both policies in one scenario, but in this one we're only implementing model period emission limit and not the annual emission limit. So you'll see it's just the 999 for the whole way. So once you have copied the values over from model period emission limit into your ClickSand file, we'll follow the same process of running that file on OSeMOSYS Cloud, downloading the result files, and reviewing them locally. Once we do this process, we'll arrive at a graph that looks something like this. And you can see by the year 2049, we still have quite a bit of emissions, and then in 2050, our emissions drop to 0. So again, we're going to copy and paste these into our results summary file. And you can see this is the model period emission limit scenario. And as we just pointed out, we have this weird effect at the end where the emissions are reducing drastically in the last year. So initially, those results may be a little surprising. However, if we come back to our exercise and we scroll down to the bottom, there is a discussion note on this. And what this discussion note is saying is that the model is following all constraints we implement to the model. However, since our model only goes to 2050, we don't necessarily have to have a resilient energy system past this point. Therefore, the model attempts to distribute the emissions throughout the model horizon rather than doing a gradual true phase out. So if we do want to fix this issue of this sudden drop-off emissions, which we probably should, it might be appropriate to pair a model period emission limit with other constraints in the model, such as build limits on capacity, or maybe also an annual emission limit in those final few years. So if we scroll back up to the top to see our learning objectives from this exercise, we will see through this exercise we have understood the different emission policy options in OSeMOSYS. So those are quantity-based emission policies and price-based emission policies. We have then implemented these policies as well through emission penalties, a yearly emission limit, and a model period emission limit. And we can see that in our results summary tables here, where we have our emission policies in the blue, orange, and gray, our annual emission limit in yellow, and our model period emission limit in green. These are the different types of emission policies available to OSeMOSYS modelers. Good luck in implementing these in your own models.